Great. Now that we know how to name alkenes and alkynes, so it's time to look at their reactions and how they are shaped. So for alkenes, you have a double bond, and of course, each carbon must be bonded to 4 bonds. So you'll expect that the carbon here has sp2 hybridization. Reason being, you have 3 electron domains for each of them. So if it's sp2, you expect that the bond angle will be 120. There, and there. It's going to be 120 degrees. And for sp2 atom centers, the molecular shape is always trigonal planar. Underline the word planar. Okay. So the bond length is 1.34, which is shorter than a single bond. And then the pi bond helps the structure to be planar. So like you see here, everything is flat. Everything is flat. So this is the ball and stick, this is the space field, and this is the electron distribution cartoon. Where there is brownish, yellowish, that's where the electrons mostly reside. Where there is bluish, that's where the partial charge is. So you would expect these hydrogens to be partially positive, and you expect this area around the double bond to be partially negative. That's where you have 4 electrons making the double bonds. Okay. Now you can see in this structure that the double bond here is flat. Whichever way I rotate it, the molecule is flat. So, and you have 3 electron domains, so it's trigonal, and then it's flat, so it's planar. You see, you cannot see the atoms to the back easily if I tilt it this way. Alright, remember we said the pi bond is made by side-side overlap of p orbitals. When there is side-side overlap, so you will expect that the pi bond is going to be weaker than the middle sigma bond. So whenever you are reacting the pi bond, the double bond with something, the double bond will open up the pi bond. So pp overlap gives you the pi bond up and down, like this shaded area. That's where the pi bond is. Now remember we said that the carbons in the double bond are sp2 hybridized. So if these are sp2 hybridized, then you'll expect that the sigma bond is sp2 because the sp2 orbitals will overlap head-head to make the sigma bond. So this bond will be sp2 type of covalent sigma bond. If you try to rotate the double bond such that you get the geometric isomer, so let's say there's a CH3 here. So if you try to rotate this bond, that should have given you this geometric isomer, where probably this CH3 on the right will be down, and now the hydrogen that's here will be up. This would have been geometric isomers. This is the cis and this is the trans. Unfortunately, this is not possible without breaking the pi bond. See how these are overlapping. If you try to do the rotation, you're going to break these overlaps, and by so doing you're breaking the pi bond. You'll end up with this structure. So this is not possible without breaking the pi bond. We discussed that in an earlier lecture. The only way you can isomerize the cis, where the groups are on the same side, see the metals on the same side, so that's where that cis, to the trans, where the metals are opposite side. The only way you can do that is by doing a radical reaction where you first break the bond, rotate the single bond, and then make the double bond back again. So that's what probably this will be done. Now you can see that here the chlorines are on the same side, so we call this cis. Here the chlorines are on opposite side, so we call this trans isomer. Both of them have the common regular UPAC name. Obviously, this is carbon 1, that's carbon 2. This is carbon 1, this is carbon 2. So it's 1, 2, and then you have 2 chlorines on those 2 carbons. So it's 1, 2, dichloro, di meaning 2 chlorines, chloro because you have a chlorine, the chlorine, dichloro, and then eth because there's 2 carbons, and E because it's a pi bond in the structure. So this will be cis -1, 2 dichloroethene, defining the geometry, because these are geometric isomers. Okay, so now here it's still 1, 2 dichloroethene, but it's trans because the chlorines are on opposite side. They will have different properties. Notice that the dipole moments point towards the chlorine, and in this case they're exactly pointing opposite on the same plane, so they cancel out. So here the dipoles cancel out. Because they cancel out, the boiling point will be lower for the trans than the cis. Of course, that's expected because here the dipole moments are cancelling out, so the boiling point will be lower for the trans than the cis. So like I said, the only way to isomerize the cis geometric isomer to the trans is by at least breaking the pi bond, and that could happen by radical means. Okay, we talked about radical process where we did the initiation, termination, initiation, propagation, termination. So it's a similar thing. So first you break apart the pi. You know, in a double bond you have the pi bond and you have the sigma bond. The pi bond is the weakest, it's the one to break apart, and you're going to break it by moving single electrons. That's why we're using the fishhook arrow, and we're moving the 2 electrons that made the pi on either side of the molecule towards the carbons that make the pi, the sp2 carbons. So you do that breaking what we call homolytic cleavage, because we are moving 1 electron at a time and we are breaking 1 pi bond. Lytic in biology means breakdown. If you do that, you're going to end up with these electrons on their respective carbons on either side. And then now, because now you have a single bond, we can do the rotation. Let's say we rotate 90 degrees. Then this chlorine will now be on the plane facing towards us. Remember, I said the shaded wedge means towards or up. But in this case, as drawn, is towards us. Okay, and then do one more 90-degree rotation. Then it's gonna go straight down. So from here to here, overall, you'll have done 180 degrees rotation. So the Cl was up, now it's completely down. And then after that's done, we bring back the electrons by sharing the 2 electrons to make the pi bond back. So now you'll have moved from the cis to the trans. That's the only way you'll isomerize pi bonds. Otherwise, they don't just rotate. Like in single bond, we said you can rotate this. You can rotate this bond, right? So if this is A and this is B, you can do the rotation, keeping the A where it is, and then the B will come up here. It's possible to do the rotation of a single bond, for example in alkenes, but in alkenes you cannot do that. Okay, so let's talk about reactions of alkenes. They undergo addition reactions where the pi bond, which is weaker than the sigma bond, will be broken, will react. So addition reactions are just that. We are adding across the double bond, you are losing the pi bond. So the pi bond will go, and then if this is the reactant, it's going to be broken apart and added across the pi bond. So that's addition. To do so, you have to do a mechanistic arrow pushing process where the E part, the electrophile part, which is going to be partially positive or fully positive, will add to the pi bond first to make what we call a carbocation. Carbocation comes from the word carbon, which is positively charged. Okay, so cation. Species that are positively charged are called cations. Species that are negatively charged are called anions. So you get a carbocation intermediate before the mechanism continues. Once you get your carbocation, a negatively charged species or a species with a lone pair will come back to attack the positive center, which is a carbocation, which is what's happening here. And that's how you get your addition product. Okay? So your pi bond opens up, picking up the partially positive part of your reagent, and then the nucleophile falls off, as shown by this arrow. Then the nucleophile that fell off will come back to attack the C+. Okay? As you open up this bond, this carbon right here will be one bond less. Remember, there are two hydrogens there, they're just not shown. There are two hydrogens here, they're just not shown. So using this bond to make a bond with E, which is this bond right here, this arrow will now be this bond in red. Okay? If you use that bond to make a bond with E, and that bond attaches to the carbon on the left, then this other carbon right there will be one bond less. So it's going to get a positive charge. Or rather, it will be one valent electron less. But you're welcome to do the formal charge calculations. You'll find that this is positive. And this is what we call the carbocation. And then the nucleophile that fell off from here will come back to attack because opposite charges attract, negative and positive. You get the product. So this is just a generic process. So let's go specific. Before we do that, let's again explain what carbocations are. So one thing you should know is that the carbocation will only have 3 bonds around it. So there are 3 electron domains. So it has to be sp2 hybridized. All these guys are sp2 hybridized, sp2, sp2. If they are sp2 hybridized, then they should have a missing p orbital or a p orbital with which is empty. You know, if you compare sp3 to sp2, the difference is a p orbital. So there's one p orbital that's empty, which is what you're showing here, orthogonal 90 degrees to the plane of the carbocation. And because it's sp2, all carbocation C+ centers are trigonal and planar. They are trigonal and planar. So if they are planar, we can draw them flat like this on the plane. The bond angle will be 120. But again, you're going to have an empty p orbital. Where the bonds are, those should be sp2, 3 sp2 orbitals on the plane, like sp2, 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 because the carbon is sp2 hybridized. So you can make sp2, sp2 sigma bond with another carbon, right? And that's what we said right here. You make an sp2, sp2 sigma bond between the carbons because both of them are sp2 hybridized. Alright, so, but you have to know the ranking of carbocations. How stable are they? Which one is more stable than the other? Here we are showing CH3s, but really it could be any carbon containing group. So I'm going to just generally say an R group containing carbon, R group containing carbon, and R group containing carbon. So there are 3 alkyl groups. There are 3 alkyl groups. So it's called tertiary carbocation. Okay, it's going to be more stable than secondary, which only has 2 alkyl groups. Why is it so? The reason is electrons will be attracted towards the C+. Remember, electrons are negatively charged. So the R groups usually donate a bunch of electrons density towards the C+. And that neutralizes the plus character, which makes the tertiary carbocation more stable than the secondary, because all we have here is donation twice through bond. That's by inductive effect. The hydrogen does not do much of this donation, so we don't draw an arrow there. Here you have one R group, so it's called primary. There's only one single help towards neutralizing the plus, and here there's nothing for the methyl carbocation. In fact, these 2 guys rarely exist. They are rarely formed because once they are formed, or if they are formed, nothing stabilizes them, like what we see here, stabilization by inductive effect, which is the electrons in the CC sigma bonds being pulled close to the C plus, helping to minimize or neutralize the positive charge. This does not work for the CH. So in this case where you have a secondary carbocation, we only can do this, showing electrons being donated to the C plus, neutralizing the C plus, making the secondary more stable than, for example, the methyl carbocation. Another way we can explain why the tertiary is stable than secondary, secondary stable than primary, is by hyperconjugation. So consider this molecule. Sorry, this should be 2. Consider this molecule. So you know here there's an orbital. Okay, there's an orbital. So if this orbital swings kind of close to what, remember I told you there's an empty p orbital here. If this orbital kind of swings towards this side, it might overlap with the empty p orbital and throw electrons in there, hence quenching the plus character of the C plus. So if this orbital at a moment swings by this side, the electrons that make the bond between the hydrogen and the carbons will kind of be shared with this empty p orbital, and that stabilizes the plus character. That process is called hyperconjugation. This is an orbital interaction between the adjacent CH bonds that can overlap with the empty p orbital of the C plus. So there are two processes that stabilize the carbocation: the inductive electron donation through bond, or hyperconjugation, where you have neighboring orbital overlapping with the empty p orbital. Okay, so if you're asked which two processes help stabilize carbocations, it's these two processes. The other process that stabilizes the carbocation is resonance. Remember I said you either pull electrons from a lone pair towards the side where the plus sign is, or the partial plus sign is, or you move electrons from a pi bonds towards the side where there's a partial plus sign or full form of partial positive charge. Okay, so that's what we have here. We don't have a lone pair, so I have to push the double bond this way. That's how you make this double bond here, and as you do that, you've stolen one bond from this carbon. It gets a plus charge. Otherwise, you're welcome to do the formal charge calculations. You'll find that there's a plus sign here after bond shift. So this is called an allylic system, or allyl carbocation, because you have a double bond next to a carbon with a plus sign. That's allyl. There's another system called benzylic carbocation, where the positive charge is sitting on a carbon. For example, this one is sitting on a carbon, and that carbon is bonded directly to benzene. Notice that it's very similar to the allyl carbocation, because I can still push electrons that way to get the resonance structure. So double bond will be here. Now the upper carbon has 4 bonds around it, so there's no longer charge there. Again, if you want to do the formal charge calculation, you'll find the answer is 0. By pushing this bond this way, this carbon here is 1 bond less, so it takes the plus sign. The rest of the double bonds stay. So you see, this is what we call resonance stabilization. And this process can continue for the benzene. I can push this one here to get the next resonance contributing structure. And because I stole this bond from this carbon, the plus sign will be here. And I can do it all over again to get the next resonance structure. See where the arrow ends? That's where the bond is formed. And because I stole this bond from this carbon right there, that carbon ends up with a plus sign, and so forth and so forth. So there's inductive electron donation stabilization of the carbocation, or stabilization by hyperconjugation or by resonance. So let's talk about reactions. Don't worry about hydride shift, methyl shift. I will not emphasize on that in this class for now. So let's talk about the specific reaction. So remember we said if you have a double bond, okay, generic double bond, and you're reacting with a reagent AB, then the reagent just simply takes away the double bond and it's broken, and it adds its elements across the double bond. So you get the addition product from the alkene to the substituted alkene. Pi bond is gone. So specifically, this AB could be a halogen, a chlorine, or bromine. And there are other types of AB. You can add HCl, HBr, you can add water, you can add hydrogen gas. These are other reactants that can play the role of AB that can add across the double bond. So for halogens, when they're added, we call the reaction halogenation. Remember, halogens are found in main group 7 of the periodic table. And in this case, only chlorine and bromine only chlorine and bromine do the best addition across the double bond. Rarely will you add F2 and I2 across the double bond. This is too small in size, this is too big in size. So the sweet spot size is that one for chlorine and bromine. So these halogens are usually dissolved in an inert solvent like chloroform or CCl4, and then you add them into the solution of the alkene. The color will change, especially for bromine. So the reaction is usually rapid at room temperature at about 25 degrees Celsius, and it's usually used as a test for alkenes. So let's say you are given an unknown liquid, and those taking 263 lab will discuss about testing functional groups. So if you're given an unknown liquid and it happens to be a double bond, and you take liquid bromine dissolved in one of these solvents, you see that this guy is brown. So if you take 2 drops using a dropper, take 2 drops from here and drop them here. As soon as the brown liquid drops into the alkene mixture, okay, the brown drops are decolorized. Okay, so why is that so? The reason is the double bond. For example, let me use this as an example. Let's assume that our liquid here is cyclohexane. As soon as you add the Br onto the alkene, the Br is broken apart and is added across the double bond, removing the pi bond, so you get the Br added across. So you no longer have the brown substance because it's broken apart before it's added on here. And then now the solution that results is going to be colorless. So that's how you know that you had an alkene in the first place, because as soon as the brown bromine drops in there, it's broken apart, and that's why it decolorizes. And this only happens whenever you have alkenes and even alkynes. So it's a test for unsaturation. Whenever you have alkenes and alkynes, same process happens, the bromine will be broken apart. So the liquid bromine is a chemical that can be used to test for the presence of double bonds, as the brown red colored bromine solution turns colorless when it reacts with the alkene. So to summarize the process of this halogenation process, for example, using bromine as an example, where the bromine will be added across the double bond. Let's use the CH2 here, alkene. So the first thing, you attack the bromine, and then the bromine is going to counterattack. So these red and blue arrows will eventually be these 2 bonds. Okay. The other bromine of the dimolecule, the other bromine falls off. So you make a 3-membered ring using these 2 arrows. Pi bond is used to attack the bromine. Bromine says, I'm going to attack you back. And at the same time, this falls off. Okay, so you make a 3-membered ring. Remember, we said 3-membered rings are angle strained because the angle in there is 60 instead of 109 0.5, because you have 4 electron domains around these carbons. So it's angle strained. 60 degrees is a very small angle. These bonds are too close. The electrons making the bonds are too close. Electrons are negatively charged. They repel. So the three-membered ring would want to repel to pop open. So to do so, the bromine that fell off will come back here to use its lone pair to attack this carbon, and this opens up. You might ask, why do we have a plus charge here? The reason is we used one of the lone pairs of bromine, okay, to attack this carbon. So you're left with 2 lone pairs, 2 bonds. If you do the FC calculations, you find that the bromine has a charge of plus. Okay, so once this attacks this carbon, the ring opens up, you get your product, which is this product right here. Okay, so the alkene reacted bromine to give you this product, losing the pi bond. And notice that I drew my product up and down, up and down. They will always be like that and not the other way around. This is the geometric isomer. The bromines are big. If you draw the one that has bromine on the same side, they're going to be sterically hindered or crowded, and this will be unstable. The molecule will immediately do the rotation because that's a single bond to give you that. So you'll see the anti-product, not trans. There's no double bond, so we don't call this trans, we don't call this cis. We say we say this is syn instead of cis. Cis, we use that for double bonds. For alkenes, we call it syn, which means same side, and anti, which means the groups are opposite side. That is probably the case whenever the reagent is symmetrical, like we just discussed for Br2, and the alkene is also symmetrical. So now what if the reagent is n-symmetrical and the alkene is unsymmetrical? There's no internal plane of symmetry. Here the internal plane of symmetry, see how I can split them apart, but here if you cut the molecules into half, they are not reflected, so they are unsymmetrical. What if you have the unsymmetrical case? Because I've just described the symmetrical case in halogenation. So now if that is the case, then you have to use a rule that's called Markovnikov rule to determine which product is mostly favored. Why do I say so? Because there's gonna be regioisomers. So for example, assume that this is a carbon containing group, for example CH3. If you're adding an asymmetrical reagent like HBr, this is not symmetrical. Br was symmetrical because you can carry it into equal half. Let's say you're adding an symmetrical reagent like HBr. Then that means that as you add them across, the H could end up on this carbon, and then the Br could end up on the other carbon, or the other way around. The Br could end up here, the H could end up here. Notice that because this is a carbon containing group, these two molecules are not the same. Why? Because you started with unsymmetrical alkene and reacted it with unsymmetrical reagent. So which of these two will be formed or will be favored or formed in greater amounts? To know that, we have to use what we call Markovnikov rule. So there's a simple rule of thumb to predict which product will be formed greatly. It's called Markovnikov rule, which states that when unsymmetrical reagent like HBr, for example, adds to a double bond of an unsymmetrical alkene, for example propene, the electrophilic part of the reagent, which happens to be the hydrogen, the electrophile are usually partially positive or fully positive. The hydrogen here will be partially positive, the bromine will be partially negative because of dipole moments. The electrophilic part of the reagent, which is the hydrogen, adds to the carbon with the most hydrogens on it. So for example here, this is the double bond. So you look across the double bond, ask yourself which side of the double bond do you have more hydrogens? Not considering this because this carbon is not part of the double bonds. So we'll compare this carbon and that carbon, those sp2 carbons. Which one has more? That's where this hydrogen will go. So it happens to be this carbon. So you will have the hydrogen you have the pi bond grabbing that hydrogen, the Br falls off, so you'll end up with now 3 hydrogens on this end. I'm gonna circle the hydrogen that came in, which could be that. Now you have 3 hydrogens, and because you use the pi bond to attach the hydrogen on the side where there is more, according to Markovnikov rule, then this carbon will be positively charged. Now remember, the Br fell off, so it's gonna be the other product. Okay, and then the Br will come back to attack because opposite charges attract, so you get your addition product. Now the Br will go on the side where the hydrogens were less, so now you'll have your Br here, and then on the other side, obviously, you have your CH3, where you added the hydrogen here, and now you've added the Br here. So there's a hydrogen that you added in there, and the Br is here. That is your addition product. So that's Markovnikov rule. Again, Markovnikov rule states that the electrophile part of the reagent will add to the carbon with most hydrogens. So this is the electrophile part, because electrophiles are partially positive, nucleophiles will have the negative charge. Electrophiles are partially positive or fully positive, nucleophiles are partially negative or neutral with lone pairs. So this is the electrophile part of the reagent, HBr for example. So that H should end up where there's more. This is the carbon, sp2 carbon that has more hydrogens. We don't consider this because that's not an sp2 carbon. We are adding across the double. So the hydrogen ends up here. You make a plus sign. This is a carbocation, and it happens to be a secondary carbocation. The bromine that fell off plays the role of a nucleophile to attack the carbon plus center. You get your addition product. So again, you're given an example here. Looking across the diol bond, following Markovnikov rule, this sp2 carbon has more hydrogens. We don't consider this even though it has 3 hydrogens. We don't consider that. So we only consider the carbons across the diol bond. So this has 2 hydrogens. So we do the attack using the pi. So you get a positive charge here because you use the pi bond to make a bond between the H and the CH2. Okay, so remember this is a CH2 here, so the hydrogens are here. So this black hydrogen is now ending up here where there was more according to Markovnikov rule. And because this carbon now is going to be 1 bond less, it takes the positive charge. The red hydrogen is still there because I told you the carbocation will have 3 electron domains, so that it stays sp2. So there's a hydrogen there. Again, you use the pi bond to grab the hydrogen towards the CH2. So this carbon on the other side, the sp2 carbon on the other side is 1 bond less, so we put the plus sign there. So the other alternative was to do the anti-Markovnikov addition. So let's say we do the opposite. So let's say we take our black hydrogen, which is this, and add it where there was less. What happens? So you're gonna get the red hydrogen here and then the one that I've circled here after the addition, and because now you did the opposite, this CH2 is gonna be 1 bond less and takes the plus sign. If you characterize, you'll see that this part here will be taken to be an R group. It's bonded to a carbon with a plus sign. So there's only one R group. Then this is a primary carbocation, while this one, following Markovnikov rule, so this follows Markovnikov rule, it gives you a C plus surrounded by 2 R groups, right? There's one CH3 here, there's another CH3 there. Those are the ones I'm calling R groups. So this happens to be secondary. So remember what we said. Tertiary is more stable than secondary, secondary is more stable than primary. And that's why we always go Markovnikov whenever we are doing addition across the diol bond, because it helps to give you a more stable carbocation. In this case, we made a secondary versus the primary, so the secondary wins. So this is what will go on to give you the final product. Okay, so next reaction is hydration. It's the addition of water across the diol bond. So for example, if you have CH2 and CH2, and you're adding H2O. This always happens in presence of an acid catalyst. Just simply take it as H and OH will be added across the double. So you're gonna end up with your CH2O, right? A H will go on one CH2, the OH will go on the other CH2. This is when they are symmetrical. But when they are not, when the alkene is not, this alkene is symmetrical. This alkene is symmetrical. But what if you have unsymmetrical alkene? It's like what we have here. The alkene is unsymmetrical. So first of all, the pi bond, remember we said that the addition of water requires an acid catalyst, right? So the pi bond will first of all attack the acid catalyst following Markovnikov rule, which means the hydrogen should go on the sp2 carbon that's more. Here you have CH2, you have 2 hydrogens. Here you only have 1 hydrogen. So you get CH2, you'll get CH3 here after the extra hydrogen is added, and you get a plus sign. Then only then, so this species is just what's shown here, only then will the water come to attack the C+. These are secondary carbocations. So it's going to be attacked by the C+. You get this intermediate. We don't want this extra hydrogen that came with the water, and the oxygen will bear a plus charge because you used its lone pair to attack. If you want to confirm that you have a plus sign, do your formal charge calculations. So another molecule of water, because water is a solvent also, there's lots of water in the flask. Another molecule of water will come and do what we call proton transfer. Okay, it's gonna take off or pull out the extra hydrogen. As you pull it out, the 2 electrons that made the bond between the O and H will be donated to the oxygen, neutralizing the plus sign. You end up with an alcohol. So this is one way of making alcohols from alkenes. Okay, so first step is protonation of an alkene in a Markovnikov fashion, where the H plus ends up on this sp2 carbon of the alkene that has more. And you make a carbocation because once you use the pi bond to grab that, the other sp2 carbon will bear a plus sign. The second step is nucleophilic attack of the carbocation by the water molecule, because we said a nucleophile will either be negatively charged or just neutral. So you see, the water molecule is neutral, but it has lone pairs that it can use to attack. Next, you don't want the charges on the molecule, so we use the second water molecules to take out the extra proton. As we neutralize the plus sign on oxygen, you get an alcohol. Okay, so simply put, start with an alkene, react it with water in presence of an acid catalyst like HCl, you're gonna get an alcohol. So you moved from prop-in to 2-propanol. The OH is on the second carbon, so it's 2-propanol. All right. So we'll continue with the reactions next time, and we'll do hydrohalogenation next time.